Welcome to a review of partial derivatives. So the general idea here is if we have a function in two variables, we can take the derivative with respect to one variable where we just treat the other variable as constant. So we can take the derivative with respect to one variable treating the other variable as a constant. So the notation, we use partial. So we can take the partial derivative with respect to x instead of using lowercase d we're used to. We use Greek letters. Technically, I think this is the lowercase Greek letter delta. Partial derivative with respect to x of some function f of, say, xy. We denote this as fx. Similarly, we can do a partial with respect to y of f of x, y. This is fy, and then we can take essentially what will be second derivatives, third derivatives, except we can change out what variable we can use. So we could take further derivatives, partial derivatives with respect to x or y and beyond, and we just keep stacking the letters next to each other, as you can see in my next example. So in this next example, we're going to go ahead and find a series of partial derivatives, second partial derivatives, and what are called mixed partial derivatives. So if we want to take the partial with respect to x of f of xy equaling x cubed y squared plus x ey. So the partial with respect to x evaluated at xy. And again, we're going to take the derivative essentially with respect to x, treating y as a constant. I apologize, my screen is not updating. Right. So to find the partial derivative with respect to x, again, we're taking the partial derivative with respect to x of x cubed y squared plus x e to the y. When we take this partial with respect to x, we treat y as a constant. So we would have 3x squared, and then y squared just comes along for the right as if it were a constant. Derivative of x is 1, and the e to the y just comes along for the right as if it were a constant. Taking the first partial with respect to y, and then evaluating it xy. We are looking at the partial with respect to y of x cubed y squared plus x e to the y. In this case, we are going to treat x as a constant. So the x cubed comes along for the ride, and y squared would go to 2y. X comes along for the ride, and derivative of e to the y would be e to the y. Next up, we're going to take the second partial with respect to x. So here we're going to take the partial derivative with respect to x of the first partial. And so we're looking at the partial derivative with respect to x of 3x squared y squared plus e to the y. And that first term, with respect to x, we'd have the x squared will go to 2x, so we wind up with 6xy squared. The second term doesn't have any x's, so it will go to 0. Similarly, we can find the mixed partial, fxy, evaluated at xy. This, we're going to take the partial derivative with respect to y of the first partial with respect to x. So we're looking at the partial derivative with respect to y of 3x squared y squared plus e to the y. This time around, x is acting like a constant. So we have the 3x squared comes along for the right, at y squared will go to 2y. So this becomes 6x squared y. And derivative of e to the y is just e to the y. I'm going to give myself a little more room for those last two second partials. So the next ones, we're going to look at the mixed partial fyx evaluated at xy. So this is the partial with respect to x of the first partial derivative with respect to y. Or we have the partial derivative with respect to x of 2x cubed y plus x e to the y. So taking this derivative with respect to x, we should get the x cubed will go to 3x squared. So we get 6x squared y. And then x e to the y, treating y as constant, we would just get e to the y. And then finally, if we take the second partial with respect to y and evaluate it at xy, we're looking at the partial derivative with respect to y of fy, or the partial derivative with respect to y of 2x cubed y plus x e to the y. And this becomes 2x cubed plus x e to the y if we're treating x as a constant. So just something to note here, the mixed partial xy and the mixed partial yx gave us the same result. So note the mixed partial where we did the partial with respect to x followed by the partial with respect to y. And the mixed partial where we did the partial derivative with respect to y first, and then with respect to x were the same. So this holds true as long as the partial derivatives are continuous in an open rectangle. So this holds true as long as f and its partials are continuous. Around the point. So one other piece of information we're going to be using in this section is the chain rule for multivariable calculus. So if we have y is a function of x, then it turns out that we can just take the standard derivative with respect to x because f of x, y is a function in terms of x. So then f of x, y is a function of x. And so it makes sense to just take the standard derivative. And the way that we can do this without actually having to plug in the function, plug in y of x, is that we get that the derivative with respect to x of f of xy is equal to the partial with respect to x evaluated at xy plus the partial with respect to y evaluated at xy times dy dx. Or in other words, times y prime. Similarly, if we view x as a function of y, then we get the derivative with respect to y of f of xy is the partial with respect to x evaluated at xy times dx dy plus the partial with respect to y of xy. So this fact is going to be key. Either version of this will be key in exact equations, which will be what we are looking at in section 2.5 and 2.6.